Mithresh, a pre-final student from Panimalar Institute of Technology. On behalf of IEEE TEMS Madras chapter and IEEE Panimalar Institute of Technology TEMS chapter, we all cordially invite you for this wonderful webinar. Today, to make this session more enlightening, today we have our eminent speaker, Mr. V. Sudharsan. Welcome, sir.
Thank you.
Mr. V. Sudharsan has completed his BE in Adiyaman College of Engineering and completed his ME in SVCE Sri Panimalar and also completed his MS in IIT Madras. He also scored his GATE score of 90.61 marks and also being a trainee of GATE exam. He has experience of 15 years. With this experience, he has come here for this today's session. I heartily hand over the session to Mr. V. Sudharsan. Please, sir.
Thank you very much. Arun sir, shall we start the lecture?
Yes, sir, we can start, sir. We can start it.
Sir, yeah. So is the screen visible? The slide I have displayed?
No, sir, no. Mithresh, can you check it? Yes, sir.
So it is visible, sir.
It's visible.
Yes, it's visible.
Visible. Okay. Thank you. Okay. So first, I extend my heartfelt thanks to Mr. Arun for giving an opportunity to present a lecture on hardware strategy about robots. And next, I thank all the participants to give me an opportunity to present a webinar. Okay. So the topic of presentation today is hardware efficient strategy for feasible pathfinding by a mobile robot. And here we are going to implement the design and Fpga implementation. So to be frank, we can VLSI implementation for path planning of a mobile robot. Okay. Going to the topic, and before discussing about this topic, let us see what is the overview about this presentation. So the first topic is motivation. So what is the need? What is the goal of this presentation, and what is the hiding factor behind this presentation? Next, what are the challenges in hardware efficient algorithm design? So what is meant by hardware efficient, and what is an algorithm to implement a robotics, and what causes the robot to navigate and move? And the next, proposed algorithm for FPGA based path planning. Okay, so when we discuss about VLSI design, okay, it encompasses different levels of architecture and design. So right from microprocessor, the forefather of VLSI design, up to FPGA, or to the latest Zodo boards, all these comes under VLSI design only. So we have chosen why we have chosen FPGA, and what is meant by path planning, and what is an algorithm, why should we go for an algorithm. Next, key elements in architecture. So what happens, what is the need, what are the various portions in a robot? Now, as a human being, why we replace the previous designs and the previous architectures by robotic element? That is very important. Next, experimental results. So only an experiment will give you a proper conclusion about how the design has been implemented, how the robot is able to navigate. So even though still a lot of researchers are going on robotics, certain experiments will reveal what is the main idea and what is the goal, and finally conclusion. Okay. Yeah. So coming to motivation. So when we design a robot, we should always understand one thing, that it is an artificial machine. It does not have intelligence or thinking about itself. So as a person, as a research person who wants to implement a design in robot, he should understand how the robot is able to navigate from one point to another in presence of obstacles. See, coming to obstacles, we can, as a human being, I can easily cross an obstacle because my eyes will reveal an object that is present, and so my thinking will help me to decide in which direction to move. But as a robot, it is simply a machine. Okay, it only understands the command given by a human being. So you need to find a feasible path so that the robot is able to navigate from one point to another when an obstacle is present. And the obstacle may be a static or an obstacle may be a dynamic. And the next, traditional approaches based on processor. Okay. So this is what the most taxing and challenging part. Okay, which processor I have to choose to implement a robotic design. The history of robots has started from the year of 1940s from Isaac Asimov when he designed a human robot with 24 degrees of freedoms. And then there came next the part of designing. What makes the robot to think? And here only the role of processors comes into picture. The processor may be a microcontroller, Arduino, where many of the students are using, and most of the robotic projects, right from school student to college student, they implement Arduino. And coming to the next part, Raspberry Pi. So which is highly implemented in ROS, which is known as a robotic operating systems. And coming to the next one, Beagle board, and now to the level of Zodo. And apart from this, we also have a processor termed as Fpga, that is a field programmable gate array. So choosing this is based on your implementation as well as how you efficiently want to design the hardware. Coming to the next one, interest in reducing area, weight, and the power consumption of the processing component. Okay, so it depends upon the application how you choose. For example, a robot can be made to implement a complex algorithm like a machine implementation or for a space navigation. For that, you have to choose highly sophisticated processors. Or in other words, a robot can you just want to do some experimental study where the robot just moves from one point to another. That's all. For that, you need not use any complex processors or devices. A simple Arduino is enough. So how you choose the components, that's very, very important, and that's very, very crucial. That is what we call it as motivation. Okay, challenges. Okay. So nowadays you can notice that many people are speaking about robotics, and nowadays a new field also has come, BTech artificial intelligence and data sciences. And do you think is it a very simple to implement a robot? It may be or may not be. For example, if you just fix a wheel on a board and if you make the board to move, you can even call it as a robot. Or if you go on to spend lakhs of money and if you implement a humanoid robot and if you're able to move, that is also a robot. But in all the cases, the algorithm and the architecture, these are very, very important. Architecture means I'm speaking about embedded architecture here. Okay, again, the algorithm is very important. You cannot simply make a robot to move here and there without any algorithmic rules. That's more important. And next, creating a program, particularly when the robot wants to navigate in a zigzag movement, is very complex. And there also comes the floating point operations and complex divisions, mathematical calculations. So you need to use certain algorithms which does not involve any floating point or division. So before going to robot presentation or robot navigation, you should be able to understand that when you want to learn robotics, you should have at least a basic knowledge about digital logic circuits. And if you have knowledge about computer architecture, it's still better. But without understanding digital logic circuits, without understanding the digital calculations, it's highly difficult to learn about robotics. Okay. So in this portion, in this presentation, I want to present briefly but efficiently what are the simple path planning algorithms, and how the algorithm has been implemented without division or floating point operations. And the next thing is mapping of algorithm to hardware. So this is the second very important point, which obviously constitutes the implementation of a robot. For example, when we discuss about algorithms, binary tree method, breadth first, depth first method, and all, we always choose a feasible algorithm so that efficiency is high. Like that, we need to choose an algorithm which can be implemented without any complex navigations. And after implementing, we should convert that to algorithm, to a effective hardware. That is what we call it as mapping. Okay, in a robotic term, mapping refers to converting an algorithm to hardware. And finally, what is that hardware? That may be a processor, that may be a VLSI. Here we are using FPGA. Okay, yeah. Let us start with the proposed algorithm. Okay, so we have several algorithms. For example, bug algorithm is there. For example, M algorithm is there, and for example, Dechek cross algorithm is there, and there is how we choose it has implemented several simple algorithms for robotic navigation. According to how we choose it, the algorithm must be implemented in such a way that the robot must not struck in the middle. Okay, so for example, the robot has to either reach the destination or it has to come to the conclusion that there is no goal or no destination at all. Okay, so when I propose an algorithm, I have to make these 2 points clear. Either the destination is reached or coming to the conclusion that it is very difficult to reach the destination. Okay, so the first step is you have to move towards the goal. Okay, so if the goal is reached, it means that there is no obstacle at all. I'm speaking about the initial movement. For example, there is no obstacle at all. So once the robot moves straight, what happens? The goal is reached, that's all. Okay, so obviously I have to either after reaching the goal, I have to stop or I have to proceed with the next experiment. But if there is an obstacle in front, so that's very important. So when there is an obstacle is in front, the front sensor has to detect, and the robot has to turn by 90 degrees to move along the obstacle boundary. Okay, so why should I turn towards 90 degrees? I should turn either towards left or either towards right. And after turning, once again, I have to follow the path. So please kindly understand one thing. When you design the algorithm, you have to design the algorithm, keep tracing the path of a robot. We cannot simply give any uneven path for the robot. The path has to be done in a very explicit way, taking into the obstacles which are present, which may be either static or dynamic. Again, once it follows the obstacle boundary, it has to proceed towards the goal. Again, for example, if it encounters another obstacle, it has to stop and it has to move towards opposite direction. And this algorithm has to be followed again and again until it reaches the destination. And once again, if the destination is not reached, okay, So again, you have to declare that there is no goal. And there is no, because sometimes they may involve a lot of complex obstacles. A robot simply cannot navigate easily. So you should design algorithm keeping all these points. The first point is a path to the goal. Next point, what happens if the path is too complex? And the third point, how it can trace the path so that it can reach the goal effectively. Okay, now I'm showing you a simple diagram based on the algorithm which we discussed now. This algorithm is also known as M algorithm. And this algorithm has been proposed by how we choose it. Assume that you have two obstacles. Okay, so what happens once it goes straight, it negotiates first obstacle, and you can notice that it moves towards right by 90 degrees, and it slowly follows the obstacle boundary. You can notice that the robot has to be in a safe position from the obstacle boundary, such that it does not uh, get jammed with the obstacle. So it traces for carefully the obstacle boundary in a safe direction, and once again it moves towards left by 90 degree, and again it moves straight and it negotiates a second obstacle, and after negotiating second obstacle it again moves by 90 degree and it follows the obstacle boundary carefully, and after it reaches the goal it either stops or continues to move. So your aim of the algorithm can be either after negotiating an obstacle, the robot has to be stopped, or after negotiating an obstacle, it continues to move. I have showed an algorithm which is very simple to understand. And here I have also considered only two static obstacles. Static means immovable. I have not considered any dynamic obstacle, and I have not considered any obstacle which is cohesive, which is circular. I have considered a simple obstacles which are static, which are able to be diagnosed by the robot easily. And you can notice that the robot is always at a safe distance from the obstacle. Okay, so that it does not get jammed with the obstacle and it does not get into trouble. So those things has to be considered seriously. So this is an example of a robot navigation, how it starts from the how does it starts from the source, and how does it reaches the goal or destination. Now, see, if you take this robot navigation, I told you that it turns by 90 degrees, it moves straight, again it turns left by 90 and it reaches the goal. I have illustrated the robotic navigation by a simple algorithm. But when I want to implement this algorithm into an architecture, there comes the most complex part of a robotic. This we call it as mapping. So what is mapping? Mapping is simply the method of transforming the algorithm to hardware. You can notice that when you learn about robotics, you will be learning about certain things which are novice to you, right? For example, M algorithm, for example, navigation, hardware efficient, and mapping. So all these things only implement an effective robotic structure. So we discussed about a navigation. I took a very simple example to show you. So this is a very simple example which any person who wants to learn about a robotic navigation can understand. And I have not included any complex obstacles here. And you can also notice that it is negotiating two objects, but it can also negotiate n objects. Now let us see how to map, how to transform this this algorithm into a hardware. So when I want to transform this algorithm into a hardware, I need three elements. One is control unit. Another one is ultrasonic sensor unit. Another one is motor control circuit. Let us see briefly and in detail how all these elements are framed. Yeah, the first thing I want to show you is what is a control unit. So that can be implemented by an ASM chart. So the ASM chart is nothing but algorithmic state machine chart. Okay, so from the ASM chart only you will decide what to perform, when to perform, and how to rotate. Okay, so you can notice that the first box depicts start and you move straight. Once an obstacle is detected, you have to count the total number of steps, and then you have to turn either left or right, and then move straight and stop if you negotiate a second obstacle. And once again you turn by 90 degrees and either you move straight or stop. So these are the conditions you have to implement in your program. And let us see how we can implement. The first thing, you can notice that you have in key elements of architecture, you have ultrasonic sensor unit. What is the purpose of ultrasonic sensor unit? See, as a human being, I have eyes. My eyes will detect an object when I move straight, when I travel in a vehicle, or when I walk. My eyes will detect an obstacle, and based on the condition, I will navigate. I will never go and hit the person, right? Unless I am not conscious. Similarly, a robot has to detect an obstacle. So, what causes the robot to sense the obstacle? It should have a sensor. From the name itself, sense. It should have a sensor. That sensor may be an infrared sensor, that sensor may be ultrasonic, or even a camera. So this is termed as the eye of the robot. And here I have an ultrasonic sensor, which is a pair of two. One we call it as trigger, and another one we call it as echo. Okay, so it works by the principle of time of flight. For example, once the first sensor detects an obstacle, it sends an ultrasonic rays. Okay, so it starts calculating the distance. So one of the classical feature of ultrasonic sensor is it consists of a inbuilt A to D converter. Okay, what is the purpose of A to D converter? The distance is analog. It should be converted to digital counts. Okay, for example, 5 centimeter must be converted to counts in terms of discrete counts. That is done by means of a inbuilt A to D converter. So which has a counter which is in that which can count up to 14 bits. So it traces an object, the ultrasonic sensor. Okay, the ultrasonic rays will trace an object. Once it traces an object, the ultrasonic sensor comes back. Okay, so you can notice that one buffer will send the signal, another buffer will receive the signal. Okay, you should notice that this total length should be divided by 2. This is what I meant by time of flight. Okay, so the one sensor we call it as trigger, that is the output. The other sensor, after detecting the obstacle, will retrace back. We call it as echo. Okay, so that's why we have 2 sensors, and the distance should be divided by 2. The reason is if the sensor detects an obstacle of 90 centimeters, it will travel by 90, again it will come back by 90, 90, 90, 180. So you have to divide by 2, that is n by 2. This is what we call it as time of flight. And it works by the principle of sound. Okay, so this ultrasonic sensor acts as an eye for the robot, and it is able to detect an object and it is able to retrieve back. And kindly understand one thing, this ultrasonic sensors, they work with the inbuilt A to D converter, because the analog distance in millimeter should be converted to discrete counts. So that's very, very important. And that's why I'm saying, if you want to learn robotics, You should have a complete or a simple knowledge about digital logic circuits, right? Coming to the next. I told you that the ultrasonic sensor acts as the eyes for the robot. It is able to sense and it is able to perceive and it is able to detect the obstacle. Now, how the robot is set into motion? One of the most important thing is motion. Okay, that is what we call as a dynamics in mechanical term. Without a motion, a robot is dead. Only we call a machine as a robot only if it is capable of moving. Either it is able to move from one place to another, or it is able to perform some navigation like a robotic arm, which lies in the same place and which is used for some industrial automation. Here, we are discussing about the autonomous robot. The purpose of this autonomous robot is to navigate and to reach a goal or to proceed by avoiding the obstacles, right? The sensors are used to sense the obstacle and it has gives information to the robot that there is an obstacle and the robot will decide whether to move or not. But how the robot moves, that's very, very important. For this purpose, we are using two wheels on the left and wheels on the right. Sometimes a third wheel will be there, but the purpose of the third wheel is for balance, for center of gravity. That is a wheel which does not have any control. We have two wheels and these two wheels are controlled by motor. That motor may be a DC servo, stepper, or a DC motor with a rectifier control, okay, with the power electronics control. So for example, why we should use a motor? Motor is a device which converts electrical to mechanical energy. That mechanical energy is nothing but a linear rotation or translational rotation, okay. So for that is achieved by means of two motors, and the motors are in turn controlled by a circuit known as motor control circuit. And this motor control circuit will decide whether the robot has to move straight or whether the robot has to rotate. Moving straight is nothing but a linear motion. When I want to move straight, both the wheels have to be activated. So the digital control is 1, 1. Okay. But when the motor has to be rotated, I have to maintain one wheel mobile, another wheel immobile. That is 1, 0. Okay. So if I want to implement that, either I have to use 1, 0. If I implement, the left wheel will rotate, 0, 1, right wheel will be rotating. Okay. So if I want to move towards the left or move towards the right, I have to control one wheel and I have to stop another wheel. And the rotation must be taken in terms of steps. So in discrete digital principles, 1 degree of rotation is equal to 8 steps. So that's why you can notice that the angle into 8. That is 1 degree into 8. So if I want to rotate by 90 degrees, 90 into 8, 720 steps of rotation. Are you able to understand? And the next, if I want to implement a distance, 1 millimeter is equal to 32 steps. So if the distance is 10 centimeter, 10 millimeters, 10 into 320. That is also converted into discrete steps, and that is given to a 2:1 multiplex, and it is given to a subtractor. The subtractor will choose whether the robot has to move straight or whether it has to rotate. You can notice that the rotation is given in multiplexer controls input. If the control is 0, you have to choose translational. If the control is 1, you have to choose rotation. So this subtractor is given to the counter, and the counter will start counting the steps and the motor control is achieved. So converting an analog into discrete rotation involves such complex principles. And here, whether the sensor, whether the motor, both are activated by a principal device, which we call it as embedded processor. Okay, so what is the eyes of a robot? The sensor. What is the leg of a robot? Motor control. And what is the brain? That is what a embedded processor. That may be either FPGA board, that may be a microcontroller, that may be a microprocessor. Microprocessor have been obsolete. We can use either a microcontroller for low power or FPGA for complex applications. And this represents the block diagram of a robotic system. You can notice from the block diagram, you have lot of electronic and certain analog devices. So we have implemented 3 sensors. The first sensor is straight, second is left, and is on right. And then you have 2 motor drives. Okay, one is the left wheel, another one is the right wheel. And exactly at the center, you have the processor. Okay, so the processor will decide what operation to perform. Okay, the processor is one of the most essential and primary element of any robotic design. Any student who is designing the robot should have an in-depth and thorough knowledge about the processors, because the processor is acting as a brain of the robot. Okay, so for example, my eyes will say where there is an obstacle or not. My leg will cause the movement, but whether I should move or whether I should not move, that thinking is created by the brain. Similarly, that the brain of any robot system is called the processor. This is what we use different terms like embedded system, artificial intelligence, integrated chips. All this comes under nothing but the brain of a robot. Okay, so artificial intelligence is nothing but the study of embedded system which is effectively used for discrete control. Okay, that's why artificial intelligence is very, very essential for robotic navigation. So here I'm using field programmable gate array as a processor. What is the advantage of FPGA? It is a reconfigurable. Okay, so even if you remove the power supply, by using flash memory, you cannot erase the algorithm. The algorithm will not be erased. Once again, if you start the robot, the algorithm can be achieved. This is not possible with the microcontrollers or Raspberry processors. So that is the advantage of FPGA. The main advantage of FPGA is reconfigurable. By using flash memory, you can retain the algorithm which has been implemented previously. And you can notice that you have certain level shifters. So level shifters is used for converting the discrete steps are required for the robot motion. Okay, and please understand one thing, the FPGA is a digital board. The motor is an analog device. Okay, so you should have a effective transformation of digital to analog and analog to digital. Okay, so that is very, very important. And you should have voltage buffers, because the ultrasonic sensors receive only 5 volts but the voltage from the battery may be 10 to 12 volts. So you cannot give a 12 volts for 5 volts. Okay, you have to regulate. So for that purpose only, you have voltage regulators. Okay, so the voltage regulators can be implemented using LM723 regulators, so that you can convert a 12 volts to 5 volts. Okay, and you can notice that the sensors have T and R. T represents transmitter, R represents a receiver. Transmitter means trigger. The ultrasonic rays will go and detect an object. Receive means echo. The ultrasonic sensors will come back and you have to calculate the distance. That distance is calculated by time of flight, right? So when you design a robotic system, three devices are very, very essential. First, the control circuit, which is nothing but your FPGA. FPGA controls everything, whether it is a motor or whether it is the ultrasonic sensor. Next, sensing the obstacle, that is done by means of ultrasonic sensors. Nowadays, people are using cameras. It depends upon your application. And third one, motion, dynamics, which is very, very important. That is achieved by means of robotic wheels, which are in turn controlled by motor control circuit. Okay, so these three, motion, planning, and control, these three are very, very essential for any robotic design. Okay, now I will show you a video how, before going that, I will show you how a robot is actually designed. What are the practical ways of designing a robot? Yeah, kindly spare for a few minutes. I will share a slide which will show you how a robot can be designed. Dear students, are you able to see this diagram, this photo?
Yes, sir.
Yeah. So you can, yeah, kindly notice that this is a robot, a complete autonomous robot, which has been designed using sensors and Arduino microcontroller and with the two wheels. You can notice that it consists of actually 5 sensors. Okay, so these 5 sensors object to detect the obstacle. And you can notice that all the sensors are connected with the 3 pins, namely for 2 pins for the sensors and 1 pin for the supply. And the ground will be common. Okay, the supply will be 5 volts, which is given from a voltage regulator. And next, you can notice that it consists of 2 heavy duty wheels. Okay, so these wheels are in turn fixed with the 2 motors, which will be present beneath the wheels, and they are used for motion. And you can also notice that the robot is fixed with the battery as well as an Arduino board, which is present at the top of the robot. The battery is provided for supply to the entire control, and Arduino is obviously the main control unit. Okay, and it also consists of a mechanical chassis. So when you want to map a robot map an algorithm, and I have shown you a experiment is performed. Kindly spare, I will share you a video which will show you how the robot is able to navigate from one point to another point and how does it senses an obstacle. Yes, please, can that I have displayed.
No, sir, it is not visible, sir.
Now, are you able to see just the photo of a video?
No, sir, nothing is visible, sir. Sorry for the inconvenience, participants. Due to some technical error, speaker has left the meeting. He will be rejoining us within a moment.
Yeah, are you able to see what I have shared?
Yes, sir, now it is visible.
Yeah, thank you. Yeah. You can see this video here. Yeah. Are you able to see the video that I have shared?
Only white screen is visible, sir.
No, no. Did you see the robot moving straight?
No, sir.
No. Now?
No, sir. Only white screen is visible.
Oh, only white screen is visible. Okay, once again I'll check. I don't know why there is a problem in sharing the videos in Google. Okay. Now are you able to see the picture of the video? Hello?
No, sir. Only white screen is visible, sir.
No, it is showing that you have shared. What about others? Can anyone say? Hello?
No, sir.
You are not able to see the video.
We can able to see the screen you shared, sir, but no videos.
No, in the screen, are you able to see the robot?
No, sir. Only white screen is visible, sir.
Okay, okay. Yeah, 1 minute.
Sir, sometimes it happens in Windows Video Player.
Oh, okay, sir. Because I want to show how practically the robot is navigating.
If possible, you can upload it on the YouTube and share the link.
Okay, sir. Okay,
Later,
sir.
we can post it at the chat box also.
Okay, sir. Okay, then I'll share the slides only now.
Sure,
okay,
sir. Sure.
Sure. Okay, students, we will continue with our lecture. So I will share you the picture of the robot while we share in the YouTube. Okay. Are you able to see the slide experimental setup?
I say it is visible, sir.
Slide is visible. Thank you very much. Once again, I want to mention you that this represents the complete experimental setup for the robot. And I showed you that it consists of, first of all, motion, planning, and control. These three things are very, very essential for a robot design. Okay, so first thing, the motion is achieved by means of the stepper motor drives, which are connected to the two wheels. One is left and another one is right. And these stepper motor drives are controlled by means of a level shifters, that is converting the analog control to discrete steps. Kindly notice that here I'm using only stepper motor. The reason is the input electrical energy will be in terms of discrete steps. Okay, that is discrete counts. That is achieved by means of level shifters. And the sensing is achieved by means of ultrasonic sensors. And we discussed in detail how it is able to sense and how it is able to detect. And finally, the control, that is the brain of the robot, which is nothing but the ultrasonic, which is nothing but your FPGA device. And kindly notice that from student point of view, FPGA is too complex. Okay, it is a reconfigurable device, and it has you can also implement a flash memory. But at the same time, when you want to achieve a simple navigation or a simple algorithm, and even an Arduino microcontroller or a Raspberry Pi is more than sufficient. Okay, so that's why I'm saying that when you design the elements for a robot, choosing the components are very, very essential. Now, coming to the experiments, you can notice that the first thing, the robot is facing the obstacle. Okay, so the robot is facing the obstacle and it is moving towards the goal. And then next, you have two obstacles and the robot is navigating in between the obstacle. Hello, students, are you able to see this slide?
Yes, sir, it is visible, sir.
Yeah, thank you. So you can notice that there are two obstacles and in between the robot is navigating. And please take care that the robot has to follow the path in such a way that it has to be in a safe boundary, which we call it as an obstacle boundary. Okay, after seeing the obstacle boundary, it is navigating towards left because it has to move in a safe direction. And you can notice here, this picture clearly shows that the robot is moving in a straight line, which is safe from the boundary of the obstacle. Okay, because the robot should not be jammed with the obstacle, and it is moving straight towards the goal. Okay, so these are the pictures. Okay, you can notice the first picture shows that it is moving straight, moving the direction of the goal. And another important point any student you should understand is the robot must face the direction of the goal. Okay, that is very, very important. So you can notice that I have to align the robot in such a way that it has to face the direction. Next, once again, it is moving in between the obstacle, and take care that you should take care whether you should move in between or you should navigate at a safe distance. You can notice at the next slide, the robot is navigating at a safe distance from the goal. And the next, the robot is taking a turn such that it is a safe distance from the obstacle boundary. And finally, it is reaching the destination. Okay, so what are the extensions? Now, I told you that you need a hardware solution. Okay, hardware solution means you can notice in these cases the robot is navigating and it is reaching the obstacle boundary and it is reaching the destination. All involves a complex or rotation of wheels. When I want to involve complex rotation, I should see that there must be a solution which does not involve any complex calculations like multiplication or division. Okay, so I have to use an approach which does not involve any floating point operations, which we call it as Cordic algorithm. And many students, please, you should learn Cordic algorithm thoroughly if you want to implement any hardware efficient solution, because a Cordic algorithm is one of the best architecture which will perform any complex calculations using only addition. We call it as a repetitive addition, and it also uses subtraction. See, kindly understand one thing. In digital systems, subtraction is performed effectively by 2's complement only. 2's complement is nothing but addition, performing subtraction by addition. Okay, so in Cordic architecture, Cordic is also termed as coordinate rotation digital computer. It performs all mathematical calculations, all angle rotations only by shift and add. Okay, so discussing Cordic is a very tedious task, but I'm saying that once you implement the Cordic, you need not worry about any floating point operation. Perform all mathematical complications like multiplication, divisions, or floating point calculations only by shift and add method. We have implemented in this robot the Cordic algorithm. You can notice in this case, in this diagram, the robot direction was different from goal. I have to rotate the robot towards the heading direction of the goal. That is achieved by means of Cordic. Okay, because rotating involves a lot of floating point operations. You have to convert the angles to number of steps. Okay, so that is achieved by means of Cordic, which will use only shift and add method. Okay, kindly understand one thing. In digital principles, you'll be using a left shift and a right shift. Okay, so right shift involves a division, left shift involves addition. Okay, that method is effectively implemented for all mathematical calculations. And now you can notice that initially in this slide, you can notice the robot is in initial position where it faces a direction different from the obstacle. But now the robot is rotating towards the direction of the goal because the goal is present in front of the obstacle. So the robot heading direction is aligned with the goal and it is moving forward. So that is very, very important because initial position, it is in a direction different from the goal. If you start the robot in the direction, it will move in a direction which is different from the goal. Okay, so you're going to rotate the robot and it has to align towards the goal. That is achieved by Cordic. Okay. And you can notice that it is moving safe direction. And again, this is the second algorithm where it moves straight considering only one obstacle. Okay. This can be achieved. Okay. So it moves towards left and it reaches the destination. And all these things are achieved here by means of a static obstacle. Now, if you want to extend to dynamic obstacle, you have to consider human beings who are moving in front of the robot. Okay, so negotiating a dynamic environment is once again a complexity because here the obstacles are not static. The obstacles may follow robot anywhere and the robot has to detect the obstacle and it has to navigate. Okay, so here the conclusion is very simple. I have developed a hardware algorithm for path planning and I have developed the algorithm to architecture by mapping. For mapping, I involved ultrasonic sensors, stepper motors for wheels, and obviously the implementation is performed by Fpga. Okay, and this approach can be extended to handle not only static but both static and dynamic obstacles. Okay, thank you very much. And if you have any questions, I was planning to share the video, but due to the limitations, we are not able to share the video. If you have any questions, kindly ask now.
Thank you, sir. Thank you so much for your valuable presentation. Participants, if you have any queries, you can post it in the chat box.
Or students, if you have doubts to ask, kindly ask. Obviously, nowadays, the goal is moving towards artificial intelligence and robotics. And so understanding these two essential principles is very, very important. So I did not involve any complex terms. I suppose the presentation is to understand the basic navigation and implementation of a simple autonomous robot, right? Please kindly ask some doubts so that I will try my best to share. Yeah, thanks. Thank you very much. Please, students, only if you ask doubt, I can understand in what way this presentation was useful. And nowadays, you know already that the entire scenario in engineering is shifted towards artificial intelligence. And for student community, you should also learn thoroughly about the latest trends and algorithms which are implemented. So the question is how India going to switch to AI? Okay, it depends upon the applications where we are going to implement. Currently, what is the scenario in AICT is that they are planning to revise the syllabus. They are planning to revise the syllabus such that every semester the students are going to learn about programming skills and artificial intelligence. Okay, so recently the AICT chairman has discussed, and he told that students still have still lack the awareness about artificial intelligence. Okay, so nowadays that's why AICT has implemented a new department known as BTech Artificial Intelligence and Data Science, and also a lot of projects are encouraged by AICT to develop using AI. Okay, so it depends on how students utilize these chances effectively. Can you come up with any other questions?
I think the session was more informative, sir. So there might not be any questions from the participants in.
And again, sir, they should have more awareness about robotics. That is, yes, sir. So students still lack some awareness about robotics, and if we give more presentation on robotics and something like quadratic algorithms, they can still understand better.
Yes, sir. It was a wonderful session, and coincidentally, it was our 7th anniversary of IEEE Panimalar Institute of Technology.
Thank you, sir.
On this occasion, on behalf of Panimalar Institute of Technology, IEEE Student Branch and IEEE TEMS Madras Chapter and IEEE TEMS Student Branch Chapter of Panimalar, I thank you for your valuable presence, and thanks especially for sharing the latest trends with the students. It was an excellent and informative session. Thank you, sir. Thank you for your valuable presence.
Sir. First, I should thank you, sir, for giving me an opportunity. So you are one of the person who always motivates me to present good topics for the students. So first, I should thank you only.
Thanks, sir. It's our honor. As a simple